Today's a really big day. Well, Luke, that is, you know, it's very unselfish of you to think about postponing calculus for 2 days so that we won't leave our friends behind. So, yeah, you are really, really always just thinking about others. Okay, so here's what happens. We're going to take a curve, and we are going to bound it from A to B. And then what we're going to do is we're going to take that curve, and we're going to spin it. We're going to spin it around the x-axis. Okay, when we find the area of a curve between the curve and the x-axis, we always talk about this really, really thin rectangle. A for the day, what's the width of that rectangle? Dx, thank you. So dx is my width. All right? And what I'm going to do is I'm going to take each slice and I'm going to rotate it around the x-axis. What? Oh, 350. Yep. Okay. So you can see that when I take this rectangle and spin it around, can you see that I'm going to get like this very, very thin disc shape, like a CD. If I have a rectangle and I spin it, it will create a oh gosh. Okay, so we we're struggling with viewing a three-dimensional shape on a two-dimensional surface. So this is a circle. As I slightly turn it, you look at it, all of a sudden you see an ellipse, right? And if you look at it straight on like that, you see a rectangle, rectangle. Okay, so that's what we're doing. And so you can tell that if I were to take this area in its full and rotate it around, what kind of shape would I get? Sure, yeah, I'd get something like a cone or maybe I don't know, the end of a trumpet or something, but it's not hollow, it's solid all the way through, okay? Solid all the way through, okay? And what we do is when we want to find the volume, we don't just rotate one rectangle, we rotate an infinite number of them. Okay, we spin an infinite number of those rectangles around. We have an infinite number of disks. Because dx, what is the width of dx? It's infinitely small, correct? So therefore, I will stack up an infinite number of these. But the idea is that what I really just need to do is I need to find the volume of just one of these pieces, okay? And so the volume of a disk I want the volume of a disk. Come on, you're the best of the best. Your AP Calculus. The volume of disk. Give me something. Close. Height times pi. Not quite. Yeah, it's like a cylinder. Come on. Pi r squared. Thank you. That's the area of a circle. So that's the area of the top portion of the disk. But then I have to multiply it by the width. What's the width? Dx. Now, we've done a lot of integration now where you understand that if I have a dx, what kind of variable do I have to have all the way through? X. And so what gives me my radius? What gives me the distance from here to here? From the x-axis to the y value, which is f of x. So the volume of each disk is pi times the quantity f of x squared times dx. Now, would you agree that this part is the area of the top portion, and that when we combine the dx, that's the volume of each disk, correct? So what we like to say is that if you want to find volume, all we have to do is bound the integral from a to b. That means we get to add up an infinite number of them, and we simply integrate the area. By using this disk method right now, we're doing basic problems today with the x-axis. We would like to say that the volume is equal to the area is pi times the integral from a to b of f of x quantity squared times dx. So these are really the same ideas. Yes, no? But does it conceptually make sense what we're doing here? I mean, we bring it back to what we've done before. So find the volume of the area bounded between y equals x, x equals 4, and x equals 0 rotated around the x-axis. So y equals square root of x looks something like this, correct? Zero, 4. So that's the area that I'll be integrating. And that's the area that I will be rotating. So when I rotate it around, that's kind of the shape that I'll get. And again, you don't have to draw the rectangle there. You could draw the rectangle here and rotate it around. And you can see the discs that will be created. This is like an Easter ham, huh? It is like an Easter ham. So, I think that the reason why people struggle with this section doesn't have anything to do with evaluating the integral. It has everything to do with drawing the correct picture And in order to extract your work and organize it, I found this to be the most helpful thing to do. I take one of those discs and I draw it over here. What is the center of that disc? What creates the center? Y equals 0. Does the function create the top part of the disk or the bottom part? The top part of the disk. So the radius is going to be equal to the distance from the top part of the disk to the middle part, which is just the square root of x. Now, there will be times where we don't rotate it around y equals 0. We rotate it around y equals 1, or y equals negative 1, or say y equals x. That's, so you got to be ready for rotations of different kinds, okay? So, there we have it. My radius is equal to the square root of x. We know that the volume is equal to pi r squared dx. My width here, is it a horizontal width or is it a vertical width? Horizontal width. So this width is dx. Each rectangle I sliced has horizontal width. The actual disk has horizontal width. So therefore, the volume of each one of these disks is pi times my radius is the square root of x squared times dx. Now that I have the volume of one of these disks, how many would I like to find the volume of? An infinite number, so we go from 0 to 4 pi. What do you get if you square the square root of x? X dx. 3 steps on your test. Number 1, the graph. Number 2, show me your work to come up with the volume of the slice. 3, set up the integral. Your 4th step is to simply evaluate the integral, which is the easy part. Getting to here is the difficult part. What's the antiderivative of x? And that will be multiplied by pi. Evaluate that. 0 and 4. Plug in 4. What do you get? 16 over 2, which is 8. So 8 pi is the exact area. Well, we're in calculus, not... We draw boxes. Oh. There. What do you think? All right. Well, let's get started on this one at least. We can go to lunch. Find the volume of the area between y equals x squared plus 1, x equals 0, and x equals 2 rotated around the x-axis. What does x squared plus 1 look like? Shifted up 1. So I'm going from 0, which is right here, and y equals, or x equals 2 is a vertical line. So I'm going to take that and spin that around, correct? So remember, as I take a rectangle and I spin it, I like to draw the exact same shape below. That's what we're getting. What shape would that be? Yeah. Okay, an anvil. I Okay. I like to think of it as like a cake pedestal. So it's wider on the bottom, it's more narrow on top, and then you set the cake on the top. I don't know. Whatever. Anyway, whatever it is, when I cut it, I get a disc. A disc is the shape I get when I slice off the ends. What is the width of the disc? Is it dx or dy? Dx. It has horizontal width. What is the center of the rotation? Y equals 0. We'll pick up when you get back from lunch. All right. What makes the top part of the disc? Yep. So that means that my radius is the distance between the two, which is simply x squared plus 1. So the volume of each disk is pi times the radius squared times dx. And I want an infinite number of those. So I will integrate from 0 to 2 pi. I'll square that out. X squared squared. Good. So the integral in the picture and everything's set up. Pi times x to the It is nice that these all start at 0, isn't it? They all start at 0. So I plug in 2 and I get 32 over 5 plus 2 to the third is 8 times 2 is 16, 16 over 3 plus 2. I'm going to make 15 my common denominator. Pi times close is 96 over 15, 80 over 15, 30 over 15. Yeah. Yep. What I generally do in that case is I yawn and I gently kind of pull the sides of my nose. It's usually a sinus issue. Okay. Another one. Find the volume of the area bounded between y equals x plus 1, 1 half x plus 1, and x equals 0, x equals 4. So 1 half x plus 1, slope of a half. So it goes all the way up to, at 4, what would it have a value of? X equals 4 would be all the way, right. So isn't that nice? Trapezoid. And you can draw the same thing below. And we will yeah, I was just thinking about I haven't heard that. Please give me more Lion King, please. Are you getting better? Good. Sure, yeah, go ahead. The reason why we're practicing this is because, again, I know you can do the integral. It's the setup, it's the picture. Because as we move forward, that's the difficult thing, okay? Because, like I said, it's not always going to be around y equals 0. It's not always going to be around the x-axis. It's not always going to be the top part here. Sometimes we're going to have a hole in the middle, okay? A lot of different things that we can do with these shapes. It's really quite cool. Okay. Oh boy. Okay, the top is y equals 1fx plus 1. So that means that my radius, the distance between these two things, is 1/2 x plus 1. The width, is it dy or dx? Dx, it's horizontal width. So I have pi times my radius, 1/2 x plus 1, 20 squared. Dx, integrate from 0 to 4, pi, square 1/2 x. 1 over 4 x squared plus x plus 1 dx. Isn't it nice when algebra is kind of just an afterthought, you know? It has so little to do with the actual problem. We're thinking of much bigger things. What's the antiderivative of 1/4 x squared? Very good. X to the third over 12 plus x squared over 2 x 64 over 12. Divide both by 4, we get 16 over 3. So pi times 16 over 3 plus 8 over 2 is, I'm sorry, 16 over 2 is 8. So pi times, that would be 16 thirds plus 12, or 36 thirds. 52 pi over 3. All right, last example. We're making really good time today. Really good time. Negative x squared plus 3x. You notice that they give us the bounds of 0 and 3. Had they not given us the bounds, we should see where this crosses the x-axis. 0 equals negative x times x minus 3. So you can see it crosses at 0 and 3. That's my parabola. And it will model the same shape, same behavior underneath. So I don't know what that is. What? Well, okay, all right. I thought it was a pistachio. Sometimes you feel like a nut. Okay, so we've got these shapes. Yeah, lemon. There you go. Good. So you slice it. If you try to draw on the end, you don't have any height, do you? So that's why I drew them in the middle. Literally, you can. Literally. No, not metaphorically, not symbolically. And so the middle is y equals 0. The top is. And so as you can see, the radius is the distance between them. The volume of each disk, Matt, you're staring scared. Takes one to know one. All right. We integrate from 0 to 3, pi out front, times what? Square negative x squared. Good job, x to the fourth. What's in the middle? Minus 6x third plus 9x squared dx. You can see my 3. If you say it loud enough. Hey! God, turn that one in. You could hear that one. Okay. What would you rather me do? Okay, whatever. I don't care. Okay, YouTube Nation, there's absolutely nothing educational coming from this group right now that you need to know. Okay, they are delaying your learning. So, these are my imaginary friends. All right. Integrate. Thank you. What's the antiderivative? X to the fifth over 5 minus. Good. Three to the fifth is 243. 3 to the fourth is 81. That's easy. Then just multiply 81 by 3 to 243. And then 3 to the fourth is 81 times 3 again is 243. And then 3 to the third times 3 is like 3 to the fourth, so that's 81. And so our common denominator will be 10. So multiply this by 2, we get 486. Minus multiply this by 10 and divide by 2, we get 1215. Plus 810 all over 10. And 46 minus 1215 plus 810 is 81 times pi divided by 10. Bada bing, bada bang. So if you look at your assignment, which is the way back side, section 6.2, page 391. But what I want you to do is just today do numbers 1 through 4. I assigned them some problems yesterday that they shouldn't be working on. Yeah, there's going to be some that they can't. Well, as stated, well, we'll turn this off.